Let's now return, after understanding the motivation behind all this, to looking at some lemmas and some theorems, which were really the key behind what Galois was doing when he traded looking at polynomials for looking at field extensions. So let's prove the following lemma. Let's suppose that f and e are both fields, and that alpha is an element of the larger field that happens to be algebraic over the ground field f. Let's define a set I, which is the set of all polynomials inside f adjoined x that have the property that g of alpha is equal to 0. Then we have this really nice association between an algebraic field element and some things that are going on inside the ring f adjoined x. So first of all, the set we've defined as I is an ideal of f adjoined x. Secondly, I is a principal ideal. It's the principal ideal generated by f, where f is a monic polynomial. If we keep with this notation, the polynomial that generates this ideal I, this polynomial f, is irreducible. The ideal I that we've generated is in fact a maximal ideal, and the polynomial f is unique. It's unique with being with the properties that it's irreducible, it's monic, and it generates this particular ideal. Because it's unique, whatever element f that we obtain using this lemma is called the minimal polynomial of alpha over the field f, and we're going to denote that from this time onward in the slides as m sub f of alpha. Now what I'd like to do is I'd like to prove this lemma, because this uses a lot of nice little things that we've learned along the way in ring theory and the study of integral domains. The proof of part 1 of this is an exercise, proving that the set I that we defined as an ideal is entirely straightforward using the ideal, I don't even know if he calls it, the two-step ideal test, which is really 3 steps. But that's really straightforward, and I wholeheartedly believe you can do it. For the second property that we have in this lemma, let's recall that if we start with a field and we adjoin x to it, that we get a principal ideal domain. And so it's automatic that we can take the ideal I and write it as the ideal generated by f for some polynomial f that belongs in f adjoined x. The only other claim that we made in part 2 was that this polynomial happens to be monic. Let's suppose that it wasn't. Suppose that we took I and we wrote it as the ideal generated by g for some polynomial g. Then because f is a field, we can multiply by the multiplicative inverse of the leading coefficient and get a monic polynomial of the same degree. And because it's off from this original generator by a unit, it's going to generate the same ideal. So really it's just that we can assume that the polynomial is monic if we'd like to. For the third part, we wanted to show that when we take I and write it as the ideal generated by f for this polynomial f inside the f adjoined x, that this polynomial is irreducible. So let's suppose that we can take f for contradiction and we can write it as g times h, where g and h are both polynomials. They're going to have degree at least 1, but we're going to assume that they have degree less than the degree of f. Now let's take this equation and let's evaluate it at alpha. If I plug alpha into these polynomials, I get 0, because we have an element f belongs to the ideal generated by I. That's what you need. You need to have this property if you belong to I. So 0 is f of alpha, and that must also be equal to g of alpha times h of alpha by this equation. However, we're working inside a domain here, and it follows that if we take 0 and we have it written as g of alpha times h of alpha, then it must be the case that one of g of alpha or h of alpha is 0. And we have symmetry between g and h here, so let's say that it's g of alpha that's 0. Then this is the criteria we needed to satisfy in order to belong to the ideal I. So g belongs to the ideal I, which is the ideal generated by f. This means that we can take g, we can write it as a multiple of f, so we can write g as f times k for some k inside f of x. However, this is going to give us a contradiction, because if we have one polynomial and it's a multiple of another polynomial, then the degree of g needs to be greater than or equal to the degree of f. However, this is a contradiction to what we assumed, because we assumed that g was in fact a factor of f, meaning a proper factor. So we assumed that it had degree at least 1, but degree less than the degree of f. So you can't have degree strictly less than the degree of f and also greater than or equal to the degree of f, and that's our contradiction. For part 4, we wanted to show that the ideal I was in fact a maximal ideal. So let's take an ideal J of f adjoined x, and let's assume that I is contained in J. And what we're going to show is that the ideal J is either equal to I, or it's equal to the whole ring of f adjoined x. So because we're working in a principal ideal domain, we can take J and we can write it as the ideal generated by G for some G in f of x. Now, because we're assuming that I is contained in J, and f belongs to the ideal generated by I, we know that f belongs to the ideal J. Since J is the ideal generated by G, we can write f as G times H for some H inside the polynomial ring f adjoined x. However, we've just worked to establish that f is irreducible, and we've just taken f and we've written as the product of two polynomials. Because f is irreducible, we conclude that one of the polynomials, g or h, that we have on the right-hand side of this equation has to be a unit, which means that in this case it has to belong to the ground field, f. In the first case, if the polynomial g belongs to the field f, then g is a unit, and we have an ideal j, which contains a unit, and whenever we have that situation, we know that the ideal is the whole ring f adjoined x. In the other situation, where h happens to be the unit, so h belongs to the ground field, then we know that the polynomials f and g differ by a unit, and that means that they generate the same ideal, and the ideal that they generate is the ideal I. So this shows that the only options for ideals containing I are just I and the whole ring, and that's enough to show that this ideal is maximal. And last but not least, what did we want to prove? We wanted to prove that f was unique. So what do we mean f is unique? We mean that f is the unique monic irreducible polynomial generating the ideal I. So let's suppose that there's another polynomial, g, belonging to the ideal I, that is monic and that generates I. Then, because f belongs to the ideal generated by I, because f belongs to the ideal I, which is the ideal generated by g, we know that we can write f as g times h. And since f is irreducible, and this time we're assuming that g is not a unit, we know that h must be the unit, and so h must belong to the ground field f. However, f and g are both monic polynomials, and if f is a constant, f is an element of the ground field, then we know that the leading coefficient of g times h is h, that element of the ground field. However, the leading coefficient of gh has to be the leading coefficient of f, which is 1. This implies that h has to be equal to 1 exactly, and in this equation f is equal to g times h, we've shown that f is just equal to g. Now, the main point of this collection of slides is we want to show we want to prove the following theorem, and I'm really going to prove this in full generality, so unfortunately this is going to be a little bit tedious to work through. However, since much of this material is not included in Gallian, I feel a little bit like I owe it to you to do these proofs as completely as I can. So let's take a look at what the theorem says. Suppose that f and e are both fields, f is contained in E, and that alpha happens to be an element of E. Then the following statements are equivalent to one another. The first is that alpha is algebraic, something that we've been quite concerned with. The second is that the degree of the extension f adjoined alpha over f is finite. And last, the statement is f adjoined alpha is a field. And when any one of these situations occurs, when we take a look at the degree of this field extension, it's outright equal to the degree of the minimal polynomial of the algebraic element over the ground field. As a corollary for this, we get that if you have f contained in E, and both f and E are fields, and you happen to have a finite degree extension, then the larger field is an algebraic extension of f. This is very useful because outright proving that every single element of the field E is an algebraic element would be ridiculously tedious and possibly impossible, depending on your situation. So let's take a look at the proof of this theorem. Whenever you're trying to prove a theorem, which is the following are equivalent theorem, what you want to do is find a nice order for the things that you're trying to prove to show that you can get this sort of circle going on. One implies the other, implies the other, implies the other, until you end up at the beginning. So for this proof, we're going to show that 1 implies 2, that 2 implies 3, and that 3 implies 1. Let's start with 1 implies 2, which is by far the longest at any rate. Maybe not necessarily the hardest, but definitely the longest. Now, to cover a little bit of ground here and to save me some time in these slides, I asked you in your worksheet on vector spaces to prove something for me. So let's introduce a little bit of notation first. Let's let n be the degree of the minimal polynomial of alpha over the field f. Again, we're assuming that in this 1 implies 2 situation, we're assuming that alpha is algebraic, and so this minimal polynomial exists. In order to save myself time here, I had you do in your worksheet on vector spaces, I had you show that in this situation, when you're looking at f adjoint alpha, it does happen to be a vector space over the field f, at the very least, and it's spanned by the set S, which is 1, alpha, dot, 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 so on and so forth, all the way up through alpha to the n minus 1. So what this is saying is, if you have a polynomial and its degree n, polynomial on which alpha evaluates to 0, if you take the smaller powers of alpha, alpha to the 0 power, alpha to the first power, alpha to the second power, and so on and so forth up through alpha to the n minus first power, that's going to be enough to generate at least f adjoint alpha. And that's really enough to show that this is a finite dimensional vector space, which is 1 implies 2. What we want to do now is we want to show that in fact a little bit more is true. The set S that we've written down here forms a basis for f adjoint alpha over f, and this will allow us to do that ending conclusion remark here, that the degree of this extension is actually equal to n, and not just less than or equal to n, which is what we have by showing that S spans. So let's finish the proof by showing that S is a basis, and what's left for us to do that was not on your worksheet is to suppose that we have a linear combination of the elements of S that sums to 0, that gives us 0, and we want to show that each one of the field elements happens to be 0 itself in order to make this happen. So let's suppose that we have this. Suppose we have a0, a1, all the way up through a sub n minus 1, elements of that ground field f, and we're supposing that a sub n minus 1 times alpha to the n minus 1, and so on and so forth, plus a1 alpha plus a0 is equal to 0. What I want to do is I want to go from here to a polynomial. I want to look at the polynomial g of x, which I'm going to define to be a sub n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. And this is a polynomial. And it happens to be the case that if I plug alpha into this polynomial, I'm getting 0. It follows from what we did before that this polynomial g belongs to the ideal generated by m sub f of alpha, that minimal polynomial over f of the element alpha, and we can conclude that f divides g. This implies either that we have the thing that's divisible by everything, which is the 0 polynomial, or that the degree of g is at least n. So remember that if you have a polynomial and it has a polynomial factor, that the degree of the factor is less than or equal to the degree of that polynomial. That's what we're saying here. However, we see just from looking at what g of x is that the degree of g is at most n minus 1, and the degree of f is n. Therefore, it's not possible that the degree of g is at least n, and it must be the case that g is the silly thing. G is the 0 polynomial, and in order to be the 0 polynomial, each one of these coefficients has to be 0 for all of the different I values. And what that means is that we've really and truly got this full basis property. We have linearly independent vectors here in the set S, and that finishes the proof that this is a basis. For 2 implies 3, this is really a nice, slick little proof, and it's not even just the proof of 2 implies 3 that's going to be used, or the statement of 2 implies 3 that's useful to us, but it's the techniques of this part of the proof. So let's let phi be a map from f adjoint x to f adjoint alpha. And what map is it? It's the map that takes a polynomial and evaluates that polynomial on the element alpha. Now, I'm not going to prove this part. This part is left as an exercise for you, but you can note that phi is a surjective ring homomorphism. I should say homomorphism. Because this is a surjective ring homomorphism, we can take a look at the kernel. What the kernel is by definition is the set of all polynomials in f of x that evaluate to 0 when we plug alpha in. And because we have a surjective ring isomorphism, we know by the first isomorphism theorem that f adjoined x mod the kernel of phi is in fact isomorphic to f adjoined alpha. And that is really and truly what I want here. I wanted homomorphism at this statement, but I really and truly mean isomorphic at this point in time in the proof. If it happens to be the case that the kernel of phi is trivial, then what we would be saying is that f adjoined x is isomorphic to f adjoined alpha, and because it would be a ring isomorphism, this would in fact be a vector space isomorphism. However, when you have two different vector spaces that are isomorphic, their dimension as an F vector space must be equal. However, we saw when we looked at vector spaces that f adjoined x is an infinite dimensional vector space over F, but we're assuming in 2 implies 3 that f adjoined alpha is a finite dimensional vector space over F. What this means is that the kernel of phi can't possibly be trivial, and so it must be non-trivial, which means, if you look at what the definition of the kernel of phi is, that there exists some polynomial in f adjoined x which evaluates to 0 when we plug in alpha. By definition, that means that I is a non-trivial ideal, and by our previous lemma, and what that tells us is that alpha is algebraic by definition. Now we can apply our previous lemma once we know that alpha is an algebraic element, and part 4 of that previous lemma tells us that the kernel of phi is a maximal ideal, and when we take a ring and mod out by a maximal ideal, we get a field. Therefore, by this isomorphism theorem, this right here is f adjoined alpha. It is isomorphic by the first isomorphism theorem to f adjoined x modulo maximal ideal, and therefore f adjoined alpha is a field. Last but not least, we need to do 3 implies 1. And 3 implies 1 gets to be the shortest proof of all, because we're going to use some of the ideas from 2 implies 3 in order to do this. So it's still the case that we have a ring homomorphism phi from f adjoined x to f adjoined alpha. And by assumption in 3 implies 1, we assume that f of alpha is a field. Now the statement, we conclude, because we have a theorem going both ways, that the kernel of phi is a maximal ideal of f adjoined x. And we also conclude that the kernel of phi is not trivial. This has to be the case because inside of f adjoined x, we know that f adjoined x is not a field. So if the kernel of phi was trivial, then we would be saying that f adjoined x is isomorphic to f adjoined alpha. One thing is a field and the other thing is not a field. So it must be the case that there really was an ideal that we modded out by there. And that tells us, that's enough to tell us that the kernel of phi is non-trivial, and by definition that means alpha is algebraic. So in other words, I'm going kind of fast through this 3 implies 1 proof because all of the ideals that we need for 3 implies 1 are covered on the previous slide for 2 implies 3. And this completes our sort of circuit that we need to prove the theorem.